I work in Amazon. I'm going to be talking about Bayesian optimization. So hope you are enjoying the summer school. So what we are going to be discussing in this talk is one of the ways you can use Gaussian processes for decision making and the uncertainties. There are many other things that you can do with Gaussian processes when you work in a context where there is an environment and you have to make decisions, and this is one of them. So some of you have already noticed that I have included a date here that is not the date of this year. So this is just an exercise to do some fast forward thinking on reminding you that you should probably register for NIPS for this date, because otherwise it's going to run over registration, something like that. Okay, so let's start with the real stuff. This doesn't work here. Okay, I'll do it with the. Okay, so at the core of what this talk is going to be about is going to be the goal of what most of the machine learning that we do is trying to reach, which is automation, right? So a lot of machine learning is automating processes, and I have brought this sentence of a British mathematician, Alfred North Whitehead, which says, civilization advances by extending the number of important operations which we can perform without thinking of them. You may agree or disagree with that sentence, but you should agree that most of the things that we do with ML is automation and trying that, right? So we are going to talk about two main things related to automation. One is how do we do automatic model configuration? And when I talk about automatic model configuration, I'm talking about given a data set with a task in mind, how do I select the best possible model to solve that task given some data and a particular class of models. And also I'm going to be talking about how do we do automatic experimental design. Sometimes we have machine learning models and we want to find the best model, or we want to find the best parameter for the model for a particular task. But sometimes we also have some physical process that we want to optimize that is very expensive, or a function that is embodied on some physical process that we want to optimize. And for optimizing it, we need to run physical experiments that are also very expensive, right? So we can have either experiments that are very expensive because they are very computationally expensive, or simply because we have to run a lab and that's going to cost a lot of money and a lot of time for us, right? So all this is going to be about how we automate and we optimize functions that are expensive to evaluate. So this is one of my first examples. So when you are doing data science, you have to go through a number of steps. So probably any of you have in mind a different idea of what a data science pipeline should look like. This is just a particular way of representing that. So when you do data science, you have some data collection, you extract some features from your data, you do some modeling, and then you have some results, and you need to do some interpretation of the results. And sometimes you have some closed loop in which, given the results and what you have learned from the data, you have to repeat over the process, and you decide to collect more data, or design new features, or you change the models, right? So in any of these steps, when you do data science and when you analyze data, you have to make decisions, right? So you have to make decisions of how many data you should collect and where you should collect those data, and you can think about doing some active learning for that. You have to decide what features you want to select, or you maybe want to decide if you want to use a neural network to extract the features automatically, or you want to handcraft some features yourself, or you have to choose the model. So all these pipelines are full of decisions that you have to make, right? And in machine learning, the way we write those decisions mathematically so we can solve them is typically through optimization, right? So in case of me selecting a model for a particular task, I define some loss function about the model that I optimize. Or if I'm fitting a GP, I have some marginal likelihood that is going to give me the best possible model given my data in a probabilistic sense. So all machine learning is full of optimization methods, right? And optimization problems. And some of these problems have some common features, right? So some of these problems look like this one, which is very, very simple to state, but as we will discuss, it's very hard to solve. So we have problems like, well, I have some well-behaved function, and by well-behave, I mean that something that in principle is continuous and differentiable. So I'm being explicitly sloppy about defining what this function how this function should be, but in principle, you can think on a function that is not discontinuous, something you can handle. That function is defined in some bounded domain. So during this talk, in most cases, we are going to be talking about compact sets in RD, in some Euclidean space, but that space can be non-Euclidean as well. And then there is some function f that is our main object of interest, which is the function that we want to optimize in that domain, right? So this is our problem. We are going to minimize this function over some domain, and this is what we want to get, right? So this xm, right? So if this function is fx is equal to x squared, we know how to do this. In school, we all learn how to solve this problem. We take the derivative, we set it to 0, we compute the critical points, and we find what the optimum of the function is. But the problem is that in machine learning, in most cases, we cannot explicitly write the shape of the function that we want to optimize, right? So imagine that now you have a neural network, and you want to optimize the mean square error of the neural network in a text set. You can have a piece of code that you can query on, from which you can evaluate which is the mean square error for a particular configuration of the neural network, but you have no way of writing explicitly this function in terms of the input data that you have and the parameterization of the network, right? So this is what we are going to do. So in most cases, in machine learning, we have functions that we want to optimize, which are explicitly unknown, and which are also multimodal as well. Evaluating these functions may be very expensive to evaluate, and this is very important here, right? So if you are training a neural network in 1 billion of images, and you are trying to set which is the best possible configuration, every time you try a particular configuration in the neural network, is going to take minutes or probably hours to get a result. So this function here, although we cannot write it explicitly, what we know is that we can query it in points in the domain, but whenever we query that function, that's going to take a lot of time, right? And that's going to be expensive. And of course, evaluation of f may be perturbed. It may be that when we run a lab experiment, because we are optimizing some physical process, we get some errors because of the experiment that we have, right? So this is the setup, and this is the type of problems that we are going to be solving. And the interesting thing here is that you have been learning about Gaussian process, and you have been learning about probability, and you have been learning about how to quantify uncertainty with Gaussian processes. All this is nice, and we are talking about probability, stochasticity, randomness, uncertainty. All this is fine, but this is basically a deterministic problem, right? So how does it fit that we talk about something that is uncertain and stochastic, and we are going to solve a problem that in principle is deterministic? So you can open a numerical analysis book and find a few ways of solving problems without talking about probability. We are going to use probability to solve it, and we're going to show that by doing this, we can be very efficient, actually, by solving this or other type of problems, right? Okay, so this is the setup. So this is one of the examples that I have mentioned already. So imagine that you have a neural network. This is the representation of a feed-forward neural network, and you want to select the number of units, the number of layers that you want to have, the learning rates, etc. Or regarding to physical experiments, imagine that you have a taxi company, and you want to optimize the number of taxis that you have. You want to optimize the routes that the taxis should go through when picking up customers in the city. These are two examples of expensive functions that you may want to optimize. But I'm sure that you all can come up with your own examples of expensive to evaluate functions, right? Things like in robotics, in control and reinforcement learning, you are teaching a robot to walk. You have to set some control parameters. Every time you set the control parameters, the robot will work in a different way. I'll be showing some examples at the end of the talk. When you do scheduling and planning compiler, you can optimize the way you write the code and your compilers. When you do new-strength design, or when you do intractable likelihoods in stats, right? These are just examples, but I'm sure that you can come up with your own ones. Okay, so imagine that you have the problem that I just described. We have this very expensive function that we want to optimize. So the first thing that you could do, and it actually can work very well in some cases, is just, well, if I have to optimize this very expensive function, I can just use previous knowledge, right? It's like, okay, so if I have to tune my neural network on image classification problem, something I can do is say, well, I'm going to just check in the literature. I'm going to check for the type of structures that people have used before. I'm going to use a similar one. So if a particular structure worked well in the past, it may not do that bad in my problem, right? And this is valid. This is what many people do, but this is not very scientific. First of all, because it's not very reproducible, right? Because it's hard to standardize in a way that we can write a set of rules so we always do the same in the same fundamental way, right? Okay, so this is the first thing we would do. What else can we do? Instead of using previous knowledge, how would you solve this problem? Any idea? Any idea? So how many of you, and don't lie with this question, have used grid search at some point in your lives? How many of you? Okay, good, good. I hope after this talk you never use grid search again. Okay, so that's one of my goals. Well, so you can use grid search, which is fine. Okay, so if you do grid search and you make some assumptions about your function, so you say that your function is Lipschitz continuous. So Lipschitz continuous mean, well, you have 2 points x and x prime that are in some domain where you are doing the optimization. Basically, this means that you can bound the difference between the outputs, right, by some distance between the inputs multiplied by some positive constant L, right? So this basically means that I can control how far the outputs are given the distance between the inputs, right? So what happens when you do grid search? So remember the previous problem that I defined, the one we tried to solve. Xm is the optimum, right? So imagine that I have a Lipschitz continuous function with some particular value of the Lipschitz constant, right, that I know. Then I want to bound the error that I'm making when I'm doing grid search, right? So look at this example. So what this is telling you is that if you have a Lipschitz function and you propose a number of evaluations and you compute the minimum of those evaluations doing your grid search, that's most of you know what I'm talking about, right? So you have your grid search. Then if you want to bound the optimum of the function by some small value epsilon, this is the number of evaluations that you need, right? So to give you an example, if you have a function that you want to optimize in which you can bound the distance between the outputs by the distance between the inputs times 10, which is not such a big change, right, in many cases. If you have an epsilon value, so you want to be closer to the optimum up to a tolerance of 0.01, and you are working in dimension 5, if you use grid search, this is the number of evaluations that you need, right? So this is absolutely insane. So using grid search gives you warranties, so you mathematically can compute how far you are going to be to the optimum under some conditions, but the number of evaluations that you need is absolutely insane to do that, right? Okay, so we know that also that our function is very expensive, so we are going to discard grid search. We can do something else that is a bit more clever than grid search, which is actually doing random search. So if I have this domain here in which I have the function that I want to optimize, I can do grid search, but if I do just random search, so if I here have like 1, 2, 3, 4, 16 evaluations, if I just draw evaluations at random, 16 evaluations at random, doing random search is going to be better than doing grid search in most scenarios. Can anyone have, does anyone has an intuition of why random search is better than grid search? What do you think? Why do you think doing random is going to be better in most cases than doing just grid search?
Because grid search in some way adding periodicity, which is unlikely.
It's adding periodicity. What else? You may miss some effect. So imagine that what is happening is that you have some sort of additive structure in the function, right? So by additive mean that you can write fx1, x2 by something like is fx1, f1, fx2, x2, right? So if you look at the marginal amount of observations that you are computing in each dimension of the optimization, where this is x1, this is x2, this is x1, this is x2, if you do grid search, in this dimension only, you are computing for evaluation, right? Because you are adding redundant information here. In this dimension, you are computing for evaluations, right? So when you do grid search, if you look marginally to the dimensions of your problem, here you are collecting 16 evaluations, right? So if your function has some sort of additive structure, and many of the functions that we want to optimize have that, doing random search is already going to give us way better results just doing some grid search. Question?
Because when you sample from here, it doesn't look like that most of the time. You have facts. It's not well.
It's not ideal. So these points are independent.
Yeah.
These points are not. So what you can do instead of doing grid search is do some high discrepancy sequence, like some lighting hypercube. And I'm going to be mentioning something that is called determinantal point processes, which is a way of doing random sampling but imposing negative correlation between the points, so you don't have that effect. I'll be talking about that later. More questions? No? OK. So I have a small game for you. So now you will have to participate. So this is an exercise for you all. So imagine that you have to optimize a function. I'm going to show you a figure in which there is a function that you don't know. But I have evaluated that function in 4 points, right? So the function has 1 dimension and is unidimensional in the interval 0, 1. The function is Lipschitz continuous and differentiable, so you already know what this means, right? And the evaluations of f that I'm going to show you are exact, right? And I want you to think for a moment in 2 questions, right? So this is the input domain, something between 0 and 1. These are 4 evaluations that I have collected from my function, right? And we want to find the optimum of f, right? So I'm going to ask you 2 questions. The first one is, where do you think the minimum of this function is, right? Given the information that you have. And the second question I want to ask you is, if you can collect a new evaluation, where would you collect it? And I'm going to ask you something else, which is, if you think that the location of where the minimum is and the location where you should collect the next evaluation should be the same or not. So I'm going to give you 20 seconds to think about it. You can talk to the people on your right, on your left, and then I'll check with you. Okay. Okay, so first question, how many of you think that the minimum of the function is right in this location? How many? 2, okay, fine. How many of you think that the minimum of the function is in this interval over here? Some people. And what about this in this interval over here? No. What about here? Okay, so most of you. Okay, so this is interesting, right? So okay, so how many of you think that these 2 things are equivalent? So that the place where you think the minimum of the function is the place where you will be collecting the next evaluation. How many of you think that these two things are the same? One? Okay, why do you think is the, what's your name?
Francisco?
Francisca, why do you think that these two questions are exactly the same?
Because you could test our assumptions that way.
Exactly, that's a very good point. So the rest of you think that these two questions are different. So can anyone tell me why?
Potentially grid evaluation, for example, might better understand the shape of the function.
So
More information out of
this is very interesting because you are saying, I have an assumption about where the minimum is. I'm going to test it with a new evaluation, right? And you are saying, I have a new evaluation, so I'm not really interested on testing the assumption that I think the minimum is somewhere in this space. I'm going to try to collect more information about where the minimum is, which is not necessarily the same thing what you're saying, right? So it depends. It actually depends. So if I only have one remaining evaluation, I may just want to test where my minimum is. If I have many more evaluations, I may want to collect more information, and once I have to collect my last evaluation, I may be interested in testing my hypothesis, right? So the answer to whether these two things are the same or not, it actually depends on in what situation you are, right? So, but coming back to the exercise, so most of you thought that the minimum of the function is in this interval here. Can any of you tell me why do you think that? Gradient are decreasing, so this is higher than this. We know that this Lipschitz continues, so we don't expect this to drop or grow radically. So what happened here is that those of you who thought that the minimum of a function is in this interval over here, I guess what happened in your brain is that given the information that I gave you, and given the data that we have collected about the function, you have created an idealized version of the function. Say, well, it goes through the points, it maybe oscillate a bit, so it's maybe the minimum is somewhere over here, right? So what I'm plotting here is just the histogram of the minimum of the function that I have generated. So I create the function, I optimize it, the minimum is here, so that's why all the mass is concentrated here, right? But there were more people in the room, and different people were thinking different things about how the shape of the function is, right? So a few people thought the minimum was here, but some other people thought the minimum was here, right? So if I do the exercise of collecting your beliefs about where individually each one of you think the minimum of the function is, I represent that like a function like this, and I collect the histogram of the minimum of the minima of those functions that I'm generating using your idealized version of it. I come up with something that is a distribution over the location of the minimum of my function, right? And this is a bit like magic, right? Because all what we have been doing here is we have started in this crazy situation in which we have this very expensive function that we don't know much about. We just know that we can query it in a few locations, and that's going to be very expensive. But given some prior assumptions about how the function looks, which is what I gave you at the beginning of the exercise, and given some data that we have collected by evaluating the function in some locations, we have created an object that is the distribution of the minimum. And you know that if you know the distribution of a variable of interest, pretty much you have your problem solved, right? We know that the hard problem here is how do you get a joint distribution over the things that you know and the things that you don't know. And you have had many talks already explaining you how to do that with Gaussian process. So imagine that instead of just restricting ourselves to the people in this room, we take the limit. We assume that we have infinitely many samples of the function that we are trying to optimize, and we compute the distribution over the minimum, not just the histogram, and then pretty much we have solved our problem, because here we have encoded everything we know about the minimum. And now we can answer the two questions that we had, right? And we can answer those questions in many different ways. we can go and say, well, you know, the mode of the distribution over the minimum is right here, right? So if I want to bet some money on where do I think the minimum of the function is, I will probably choose this location over here, right? Or I can do something like what I want to do is to collect a new point that is the most informative in the sense of that improves the most what I know about the minimum. I can collect a point that maximally reduce the entropy of the distribution over the minimum, right? So now I can take the distribution and to do a lot of things with them. In particular, I can answer the two questions that I mentioned before. Question over here?
Is this analytical to find the minimum point of X?
No, it's not. And that's an issue. And that's why when you do optimization like the one we are going to be doing, you may be interested on using the distribution over the minimum, or you may be interested on using other things to drive the search that we want to do. But I'm going to say later, I will explain why this doesn't close form, but how you can approximate it. It doesn't close form. It can be hard to approximate it, but there are ways of doing it. Any more questions at this point? No? Okay, good. So the general idea that we are using here is the idea that Rich mentioned in his talk about surrogate modeling and uncertainty quantification. So we have an object that can be the result of a simulator, the result of some machine learning model, some very expensive model that we don't have access to. We are going to replace that model by a Gaussian process we are going to work with because we know it's very fast, we have gradients, we can compute things, we can calibrate uncertainty, and we are going to make decisions about what happened in the real world by using the machine learning model that is able to predict what happens in the real world or what happened in the simulator that we may be using for that. Interestingly, what we are doing here is we have, remember that at the beginning we have this problem that was a deterministic problem, that is an optimization problem, right? The way we are going to solve this problem is by selecting a few locations where we believe we are going to learn a lot about where the minimum of the function is. So in a way, what we are doing is we are transforming an original optimization problem in a decision problem, right? And now each one of those small decision problems, or where do I select my new location, we are treating them as inference, right? So we are taking an optimization problem, we are making it a decision problem, and now each one of those decision problems, we are going to solve them by using everything we know about inference, right? And the reason why we are doing that is because we are going to use the uncertainty, and we are going to quantify the uncertainty about the values of the original function in the different points in the domain with Gaussian process and make decisions about that, right? Okay, so in this case, we are interested about optimizing the function, right? But what you need to have in mind here is that Bayesian optimization and optimizing the function is just a particular case of the many more things that you can do thinking this way. So you can think about the optimum of the function as a latent property of the function, or a latent property of the model you are using to analyze it, right? But imagine that instead of being interested on the uncertainty of the minimum of the function, you are interested on the value of the integral of the function, or you are interested on minimizing the error that you make when you make predictions about the function. Or imagine that you are interested on computing the maximum value of the gradient, right? All these and later properties of the function that you are working with, right? And this game of taking this original problem, transforming it into a decision problem, and solve these decision problems using inference, you can apply it not only to optimizing the function that you have, but to learning more about any latent variable that is related to the function that you have, right? So this is what I'm trying to represent with this slide. When you do Bayesian optimization, the quantity you are interested on is the cumulative regret, right? So you have a sequence of evaluation, x1, xn. If you knew f, you could evaluate your objective in that sequence of evaluations, compute the difference with the f evaluated at the optimum, and compute the regret. The smaller the regret, the better my algorithm is, because the optimal case would be having an algorithm in which from the first evaluation I hit the optimum, so the regret will be 0, right? So if I do optimization, this is what I should be optimizing, and this will be my target, right? If you are doing integration, your target will be different. If you are doing reinforcement learning, you will have some reward given some actions that you will observe after some episodes of some simulator or some dynamical system moving, right? So this is basically the idea. So this is just to put in context what Bayesian optimization is. And now I go to defining the standard and canonical Bayesian optimization loop, which you already have in mind, given what you know. So you choose some prior measure over the space of all possible objectives, right? So this is what prior you select. You're going to select a Gaussian process by default, but you can use any method that will allow you to do that, right? You are going to combine that prior belief with some data that you are going to be collecting about your function, and then you are going to define some acquisition. The acquisition is simply going to take the model that you have and define a policy that will allow you to collect new evaluations, and you are going to select that policy in a way that you think is going to be the best to optimizing that function, right? We're going to be talking about, how many of you know about the exploration exploitation trade-off, right? So not every you. So pretty much these policies, these acquisition functions are a way of balancing how much should be I exploring, how much should I explore my domain, what you were saying before, I want to explore because I want to learn more, or how much should I exploit? How much should I just test my beliefs about the location of the minimum in this moment in the optimization, right?
Good question.
Yep.
So we've been talking a bit about maximizing the evidence lower bound. If
Mhm.
we are doing that, are we implicitly in this framework you're discussing already, or is this something extra we involve?
So when you maximize the evidence lower bound, you have gradients about that lower bound, so you can use it. Here, you don't have gradients, and you assume that this is very expensive to evaluate. You could potentially use it, but you need to carefully think if this is the best thing to do. If you have a function that is very, very, very cheap to evaluate, you will never do this. You can do grid search. If it's very cheap to evaluate and you have gradient, you don't need to do Bayesian optimization. But if your function is very expensive to evaluate, that's where you need to use this. Okay? More questions? No? Yeah.
Actually, the regrets that you showed in the last page.
Yeah.
Actually, that is not Bayesian, isn't it?
Sorry?
So that doesn't count on the uncertainty measure about the.
No, it doesn't, but it's the criterion. So when you do learning theory, you want to what you want to do is to minimize the integral over the loss function, assuming that you know the true function that you are fitting, right? You cannot do that, so what you do is the sample version of it, so you can have something that you can compute that in the limit optimizes what you have. So what you do with the cumulative regret is to set which is the value that you get out of each evaluation in the optimization, right? So what you're saying is, like, in the same way you do reinforcement learning and you have some reward function that determines how much you want to explore, how much you want to exploit, given the rewards that you get at each step of the episode that you are running. The regret is telling you how much you value short-term rewards or long-term rewards. So something you can do is, instead of optimizing the cumulative regret, you can optimize the final regret. You can say, you know, I don't mind about the regret while I'm collecting new points. What I just want to do is, in the very last evaluation, I want to be very, very good. So the policy that you will do to optimize the final regret versus the policy that you use to optimize the cumulative regret will be different, because your objectives are different, right? It's a way of writing mathematically what do you mean by transforming optimization by decision, right? More questions? No? Okay. So we have described the two key elements of Bayesian optimization. One is the measure over the functions or the model, and the second one is the acquisition function, right? So now what we're going to do is we're going to visit both of them. We don't have to spend so much time on the model, because by default, most Bayesian optimization methods use a Gaussian process, and as I said before, you can use other models as well. So this is my one-slide representation of the Gaussian process. So you have your prior. This is representing your belief about your function. This is like the samples that you are generated about the function that we are optimizing. This is the posterior, so I have marginalized out the samples that go through the data points. And as you already know, marginally, this is multivariate Gaussian. So if I look at this stochastic process in a finite set of points, what I have is a multivariate Gaussian, and multivariate Gaussians are nice because they allow us to represent uncertainty and also to compute pretty much everything we need as operations in linear algebra. And we know how to do linear algebra operations very well because we know how to do linear algebra with computers, right? So this is great. Okay, so exploration and exploitation. So this is the way I was explaining, and we are getting close to lunch. So this is probably an interesting slide now. So imagine that you go to a restaurant and you have to decide what do you want to have, right? What food do you want, right? So in your mind, you have some reward function for any choice that you have when you go to the restaurant, right? So you can have burritos, you can have tacos, you can have quesadilla, right? So you have some prior belief about that. And it may be that you have been in this restaurant a couple of times before, right? So it may be you even have data about the restaurant. So you have a model that is a prior belief about how much I like going to Mexican restaurants, and some data because I have been before, right? So but now it comes to the moment where you have to choose what do you order, right? So now you can explore. You can say, well, there are parts of this menu I have never tried, but I want to explore because maybe there is something good there, but I don't know. Or you can exploit, and you can say, I'm going to go and I'm going to select the things that I like the most, right? Because I don't want to reach. So the exploration exploitation is what is encoded in pretty much any decision that you make, and also the way Bayesian optimization works. So I think this is one of the most fascinating aspects of Bayesian optimization, that encodes very well the way humans make decisions. And this is, so if you have time, I recommend you reading this paper. This is an IPSE paper in which what they did, they were running some lab experiments in which in one-dimensional problems, they were asking people to select points to optimize a one-dimensional function, and they compared this with different optimizers, and the humans were in one dimension way better than any optimizer, finding the location of the minimum. And what was the method that was the closest to it was Bayesian optimization, actually. If you think about it, when you make decisions when you go to a restaurant, it's pretty much the same thing that you are doing when you are deciding where to select the new location to optimize your function, right? Okay, so we have talked about the model, and now we are going to talk a bit about the policies, right? So how do I use my model to define what in Bayesian optimization is called acquisition function? So whenever I can collect a new location, I can make the best out of it, right? So this is one of the most intuitive acquisition functions, and it's an acquisition function that represents very well what we were saying before about the balance between exploration and exploitation, right? Because you work with Gaussian processes. Gaussian processes are generalization of a multivariate Gaussian, which means that you can characterize them by the first and second order moment, by the mean and the variance. The relationship between the moments of the Gaussian and the elements that you need in Bayesian optimization are one-to-one. The first order moment, which is the mean of the Gaussian process, is going to define the exploitation, right, that you do. And the variance is going to define the exploration, right? So imagine that you go to the extremes and you say, I'm going to be purely exploitative in my next location. So what you would do is you will go and you will take the value where the minimum of the GP is, right? That will be the policy that you will be using. If what we want to do is to explore, you would say, I'm going to go to a point in the domain when my variance is very, very large, so I can try to see if there is something interesting going on there, right? So that will be what you would do if you want to explore, right? But all acquisition functions are basically different ways of combining exploration and exploitation in one single expression, right? So here I'm representing the model, the Gaussian process model fitted to the data that we had before, and here what I'm showing is acquisition functions. I'm going to show different figures, different acquisition functions in which maximizing the acquisition functions is always better. So maximizing this function over here will give you the point that you should be collecting next. So the lower confidence bound in this case is, because we are minimizing, is minus the mean plus the standard deviation, right? So where if I was maximizing, this will be plus the mean, because I'm minimizing it just minus the mean, right? And I'm plotting in the inverse, right? So if you see, basically the acquisition, this is the acquisition function, right? So if this is the 95% confidence interval or whatever confidence interval that corresponds to values of that parameter, this is my acquisition, right? So what I am using is, I'm using a lower bound of my function given my model as the acquisition function that I have, right? And this is what I'm plotting here with a minus on top, right? So in this case, if I use this acquisition function, I will be collecting the next evaluation here. So I'm exploring a lot. I'm selecting a point which I have a large degree of uncertainty, but given my model, this is the best evaluation that I have collected, but samples can go through these points, right? So it may be that something interesting is going on there, right? So this is the upper confidence bound or lower confidence bounds and you are minimizing. So this acquisition function is interesting. It's not super widely used in practice, but it's very interesting because you can do a lot of reasoning about how you can bound the cumulative regret that I was mentioning before as soon as you collect more evaluation. And the reason why you can do that and you can write theorems like this is because your acquisition is a lower bound of the function that you are trying to optimize if you have exact evaluations, right? So if you can bound the function, you can bound the minimum of the function. And that's the reason, assuming that this Lipschitz continues. So that's the reasoning that is behind this theorem. So we are not going to go into the details, but this acquisition function is very handy to learn how far you are from the optimum given some assumptions that you make about the objective, right? So this is the lower confidence bound. Let's go and check another acquisition. So this is expected improvement. So this is if the Gaussian processes are the default choice for the model, the expected improvement is in general the default choice for acquisition functions. And now there are a few libraries out there that implement Bayesian optimization. They all have this as the default choice, right? So what is the expected improvement doing? So the expected improvement is saying, well, look, this is the model that you have. So let's reason about where should I collect my next evaluation. So this is my best evaluation. So I'm going to compute in expectation how much I can improve if I collect a point in the domain. So if I collect a point here in expectation, my model is telling me that you are not going to be able to improve, right? But if I collect a point here in expectation, what my model is telling me is like, well, because you have many samples over there, if you can compute for a point in the domain how much those samples improve your current best, then you average across that, and you know you can do that because you have the posterior distribution given a location in the space, and you have it in closed form because it's a Gaussian process. So you can come up with an expression that you can write analytically to compute how much you are going to improve in expectation the current best evaluation that you already have, right? So this is what we do, something that is very reasonable. I'm going to try to collect what in expectation is going to be the best with respect to what I already have. And this is the expression of the expected improvement. And this is what the expected improvement is telling us to do. So the expected improvement, as you can see, is less explorative than the previous acquisition because it's not saying go here where you have a very large uncertainty. It's saying, well, go to a place where the uncertainty is large, but stay close enough to the current best that you have because we know that something interesting is going on in this region, right? So the expected improvement is balancing exploration and exploitation in a different way as the lower confidence bound was doing before.
Does it have a nice knob like a beta on the previous slide?
Say again?
Does this also have a
nice knob like the beta on the previous slide?
So the beta in the previous slide, that's a good question. The beta in the previous slide is what is telling you how much do I explore, I exploit, right? So this beta, to satisfy, so in the paper where they propose this beta is related to the number of evaluations that you have already collected. So the value of this beta changes in each evaluation. And it changes through some criterion that is written here, right, to satisfy the fact that you want to minimize the cumulative regret. So that beta and beta acquisition function is nice to do the theoretical analysis and is adapting the exploration and exploitation in each evaluation. In the expected improvement, that balance is already given, right? So because of the definition of the expected improvement, you are already defining which is the exploration and exploitation. In the upper confidence bound, you are based on some criterion that is described in the paper to satisfy the theory that you want to prove, what beta you should be using here, right? Also, you see here that the expected improvement is more exploitative than the upper confidence bound for whatever parameter I was choosing before. And this is one of the main effects of the expected improvement, tends to overexploit. So when you have a really complicated problem, you use expected improvement, you may fall in some local minimum, right? So what people do is say, well, no, I have expected improvement, so I'm going to add some regularization parameters so I can make it a bit more explorative, right? This is a bit of a hack, but you can explain mathematically why this makes sense, right? So at the end of the day, different problems will require different levels of exploration and exploitation, right? And it's completely up to you, and it's part of the modeling exercise, and it's part of running the right experiments to decide which acquisition is going to work better in each problem. So I'm showing you the different acquisition, and if you read Bayesian optimization papers and people proposing new acquisition functions, you will see experiments in which you say, oh, I'm proposing this new acquisition function is better than anything in the literature. That's not true. So there is no single acquisition function that is going to outperform other acquisition functions in any experiments of a benchmark, simply because each acquisition function is representing a different balance between exploration and exploitation. And depending on how complicated the problem is, how many local minima do you have, how flat is, how non-stationary the function is, that's going to require different levels of exploration and exploitation, right? So you may find acquisition functions that work better in a wider class of problems, but you're never going to find the acquisition function that works always the best, right? More questions?
Can you speak to, it seems like we're holding the balance between exploration and exploitation constant over the number of evaluations.
Uh-huh.
Why aren't we varying that balance? Why aren't we starting out more explorative and then becoming exploitative?
That's a super nice question, and there is a very fundamental way of doing that. And if I have time, I'm going to be talking about that, which is thinking non-myopically about the problem. So all these acquisition functions have something in common. All these acquisition functions are assuming that your next evaluation is the last one, right? And that's not necessarily true. So you typically have a budget that you have to run your optimization. So say, look, I'm going to solve this problem. I have 10 evaluations, right? So if you think about using the number of evaluations that you have as something in the way you decide where you collect your points, then you have to come up with an acquisition function that is not just optimizing some expected improvement in the next evaluation, but is also taking into account the impact in future evaluations that your next evaluation is going to have, right? But this is hard, because for that you have to predict the future of what is going to be the outcome of your function and what are going to be your next evaluations, to do this rollout to the future and then to roll back to make the decision. The problem is that when you do that, that's beautiful, because then automatically you come up with acquisitions that balance exploration and exploitation. And coming back to the example of the restaurant, if you are going to the restaurant and you know that you will be able to go to that restaurant many more times, you can allow yourself to explore more because you know that you can come tomorrow and have the thing that you like. If what you got today, you didn't like it. But if you are leaving the city and that's the last time you are going to the restaurant, maybe you want to exploit more because you really want to optimize and you really want to have a good outcome of experiment that you're running. So thinking non-myopically about the problems, thinking about how your next evaluation influences the future policy is a way of automatically coming up with acquisition function that balances exploration and exploitation. Yeah. More questions?
On the previous slide,
Yeah.
the bottom graph, you have to evaluate it at a finite number of points as well, right?
So not necessarily, because you have a close expression for this function over here. So if you want to optimize this, you can run a gradient descent and optimize it. So that's all we are doing with Bayesian optimization. So you are replacing a problem with certain characteristics, and the main one is that we don't have access to the function, we don't have access to the gradients, and the function is very expensive to evaluate. But a sequence of problems in which we know pretty much everything about the function that we want to optimize. This has closed form, we have gradients, so we can do MC here, we can start in multiple locations, run local optimization. So we can take the textbook in optimization and apply it here because this is a standard non-convex optimization problem, which may be hard, but it's put us in a better position than before. Question?
But I think in general the Gaussian process acts like this, is that it kind of all the realization go through this one point, so it has much local maxima. So wouldn't you run into that problem when you're doing gradient-based optimization?
So what do you mean? Are you talking about here or about here?
About the graph down below.
Uh-huh.
If you're doing gradient-based optimization over there, wouldn't you, like a lot of times, expect many local maxima?
Yes, you would do that. And that's a problem. And that's one of the things that people typically don't talk about when explaining Bayesian optimization. And that's very important because all the theory, everything that you are doing with Bayesian optimization relies on two things that can be hard, which is first, that your model is right, or sort of right? And the second one, in that you are able to optimize this acquisition function, right? So your model can be better or worse, but at the end it will be as good as any other model that you use for anything else, right? So at least we have a model that will allow us to do this, and that a model we believe in, right? But we know it's not going to be the right model. It's going to be a model that will work for us, right? The second one is I should implement enough tricks in my optimizer so I make sure that at least most of the time I get the global optimum of this, right? And I'll show you an example. This is actually not that bad situation because here you have 3 minimum. Well, if you don't hit this one, you will hit this one, you will collapse this uncertainty, and probably in this iteration you will collapse this one, right? But as soon as you progress in your optimization, you will see that you have very concentrated acquisition functions that are flat in most part of the domain, so any gradient optimizer is going to stop. So you need to make sure that you hit the mass where the acquisition is. But people have been working on that, and there are a few libraries there where these things are handled relatively well. Okay. Yeah.
It might be a naive question, but it sounds like there are hyperparameters or parameters involved even with the optimization.
Mm-hmm.
So do you need to run an optimization on the optimizer?
That question is not naive at all. That's a very good question because what you are telling me is like, hey, okay, so look, you are telling me this problem is very hard to solve. Fine. And now you are replacing this problem with another optimization problem that is easier to solve, but that we can handle better, right? But we have been talking about optimizing the marginal likelihood in GP. So you are changing this optimization problem by other optimization problems that may not be easy, right? And that's completely right. And the way you should handle that is you shouldn't optimize the hyperparameters of this model. What you should do, you should marginalize them out, right? So you should have hyperpriorities over the hyperparameters, draw samples, and to come up with average acquisition functions over the values of those distributions of the hyperparameters given the data. That way, you don't need to optimize this thing here. And that way, you are going to see how the results that you get are way better. There are papers in which people have compared marginalizing over the hyperparameters versus doing maximum likelihood estimation. Marginalizing is typically better, especially at the beginning, because you don't know much about your function. So you want to handle the uncertainty that you have about your model, and you want to propagate that through to the acquisition that you have.
But if the error surface is more complicated than the function that's being generated itself, would that be an issue?
Sorry, second?
If the error surface is more complicated than
Mm-hmm.
the function that you're trying to solve for.
So if you have a very large uncertainty, your uncertainty over the hyperparameters is very large, that means that you need to collect enough evaluations so you can collapse it a bit until your model becomes informative for the search. Something that you do when you do Bayesian optimization, you don't start from one point and you move farther. You start with a random sample of points that you use to initialize your model, so you make sure that you start with a model that can tell you something meaningful. Because if you only have 1 point, basically your model is going to fall back to the prior in most of the input domain, so your acquisition is going to be flat anyway. So you need to give the model some information about how the function looks before it starts doing something minimal here. So look here, I have already given 4 evaluations, and we see how these acquisition functions make sense, right? But if you only have 1, you don't know anything yet, right? So that's a very good question. More stuff? No? Okay. So expected improvement, Thompson sampling. So another thing you can do, you can use Thompson sampling. How many of you know Thompson sampling already? Okay, so a few of you. It's like, I'm going to use an stochastic. All the 2 previous acquisition functions were deterministic acquisition functions, right? So given the model, I can write exactly how the acquisition looks, right? And given the same model, I will always make the same decision, right? This is an stochastic acquisition function. And the only thing I'm doing is I draw a sample from my GP and minimize it, and I collect a point where the minimum of the sample is. That's it. In this case, because I'm taking minus the sample, I will be collecting a sample somewhere over here, which is very close to the optimum, right? Yeah?
To choose a function, one function out of GP.
You draw a sample. So in the first lab, you were drawing sample from a GP, right? So you draw one sample, you optimize it, and you get that location. And you can get pretty good results by doing that. But this has a problem. Which is the problem? Here.
Sampling very close to the point you already have.
Say again?
Sampling very close to the data point you already have.
But that's a property of the sample that we are drawing. What's the problem with the method itself? So, yeah. Any idea? The sampling, it's expensive. So why? Okay, the question: why am I cheating when I plot this? The sample is finite. Who said that? Cool. That's the problem. So we have been talking about acquisition functions that were nice because we had closed forms. We can draw. We can use gradient descent. We know everything about that. But now we are talking about a way of solving the problem in a finite set of points, right? So I'm drawing here, I don't know, I think 100 points. I'm sampled from a multivariate Gaussian in 100 locations, and I'm making this line over here, but this is actually wrong. I'm cheating because this is a finite set, right? So then this is one-dimensional. So what happens if I'm solving an optimization problem in 10 dimensions? I'm going to fall in the same problems that I had when I was doing grid search with my samples, right? So the locations where I'm going to be taking the samples are going to be very far apart. And if I optimize my acquisition, I can only optimize my acquisition in the locations that I sample. So that's not going to be very nice, right? So what I can do, though, is, well, I cannot draw continuous exact samples from the GP, but I can draw approximate samples, right? So something I can do, and someone mentioned it in some of the talks, I can use, if you are using a stationary kernel, you can use the Fourier basis representation of your GP. You can come up with an approximated representation of your GP in some basis of function, and then you can draw for the coefficients of that basis of function representation. And that you can do that because of the Bohren theorem, because when you have an stationary kernel, you can represent that like a Fourier transform of positive measure, right? Where the measure for a Gaussian kernel is going to be Gaussian, so you are going to have a representation of the GP in terms of a basis of function, that a finite set of functions, which means that it's going to be an approximated, because in the GP you're going to have infinitely many of them. So you are going to draw a few of those, draw from the coefficients, generate a continuous but approximate sample, and optimize that one. And if you have a large enough basis of functions, the approximation is going to be good enough that will allow you to do the optimization using continuous, what is called continuous Thompson sampling, or probability matching, right? Okay? So that's another way of doing it. And then we have entropy search. So we mentioned this at the beginning. Entropy search uses the distribution over the minimum, or the approximated distribution over the minimum, to collect the new points that maximize the entropy, that minimize the entropy of the P of F min, right? So the way you do that is, so this is the way of characterizing the distribution over the minimum. There are different ways that you can compute entropy search. You can actually use continuous Thompson sampling, generate samples, optimize them, and come up with a smooth version of the histogram that we drew at the beginning of the lecture. Or there are other things that you can do as the methods that are proposed in the original paper where the entropy search was proposed by Philip. Okay.
Sorry, what is the
Sorry?
what kind of thing do you want?
So this is the Heaviside function. So this is the formal way of writing the distribution over the minimum. So this is the object that you need to approximate in order to compute entropy search. So basically what you are doing is you want to compute the point that with certain probability is going to be the minimum, and what you do, you can write this in terms of a Heaviside function, but that doesn't have closed form given the GP that you have. So you need to approximate this because you cannot handle directly, and you can do it through sampling from the GP.
Well, what is that in this case then?
Sorry?
What is that in this case?
Theta?
F.
F is the GP model that you have,
But
right?
then how does it correspond to entropy?
So this is the distribution over the minimum. What you use in your acquisition is this thing over here. So given that you have the distribution over the minimum or approximation of it, your acquisition function is the entropy of that distribution, is the reduction in entropy given a new location, right? So this is the entropy of the distribution over the minimum at the moment in which you are doing the optimization, right? And now you consider a new data point, right? That will give you some y, because you don't know this y yet, but you know the posterior of the GP. You compute this in expectation. So this is the entropy of the distribution over the minimum and the expectation of it for all possible outcomes that you could have given the location x. And your final distribution, for your final acquisition, is the entropy that you currently have minus the entropy that you would have if you were sampling at x.
I don't think it's closed at all.
It's not closed. No, it's not closed form. You have to approximate this. This is the definition of the acquisition. Another problem is how you compute it. Right? So I'm not saying that you can compute this in closed form. You definitely cannot do that. But this is the definition. This is what you want to do. The reasoning is I'm going to collect the point that is the most informative in terms of how much I reduce the entropy over the distribution over the minimum. And if I believe in my model, and if I believe that I have a reasonably good approximation of that distribution, I believe that this is the best I can do, which is a choice. You can decide that expected improvement is better. Right? Okay, so this is just a plot to show that different acquisitions, what I was saying before, different acquisitions give you different performance, right? And if you see Bayesian optimization paper, you typically have this type of figures. in these figures, the plot is not very clear. It's very small. I just want to give you like a flavor of how you present results in Bayesian optimization. You typically have the number of iterations versus the cumulative regret or the current best, and you have the comparisons across the different methods. And the only thing I want to show with this figure is that in different problems, different methods are going to work differently, right? And if you do Bayesian optimization, you should always include a random search in the comparisons, in the experiments.
Those graphs, what does like the regions around the graph then?
Yeah, my fault. Yeah, so this is the number of evaluations that you have.
But the regions, so you have the line, which is probably hard to confirm.
So this is the current best that you have.
Yeah, and the band around it?
Is the confidence interval. So you say what you do is, that's a good point. So you run multiple experiments, typically with different initial locations. So you make sure that the initial location doesn't influence too much the method that you are using. Because if you start different methods from different initial location, and the initial location is good, you may fool yourself thinking that the method is better, but it's simply because you started from a better point, right?
So these are the plots for regression, regret measure.
Yeah, so the y-axis can be different things. Some people plot the current best that you have at each iteration. Some people plot the regret, but they all look the same. So there is not a consensus of what you should be plotting. As soon as you plot a measure of how your algorithm is evolving in time and doing better.
They guarantee optimality, because I thought like when it comes to the correct strategies.
You cannot guarantee optimality. You can only bound the regret in the lower confidence bound. Good.
Just to get a rough idea, how many iterations did you run on these?
So it depends. The assumption in Bayesian optimization is, well, my function is very expensive to evaluate, so I'm going to run as many as I can, right? And then I'm going to compare. But if you are doing benchmarking, so you should run enough evaluations to see how the curve converges to something, right? So as soon as the curve becomes flat, you can make the assumption that it's not going to move for there because the uncertainty is collapsed, and this is the final result. But it depends on the experiments. But
How should I interpret that there are very large steps?
the steps is that, so if you have collected a point that is good, right, and you are exploring, and while your exploration you are not finding anything interesting, the current best is going to be the same, right, while you are doing the exploration. If at some point you hit a point that is better, then you will contribute to the curve. Your curve will go down, and then you will keep exploring until you find something interesting.
So, how long do you have to wait till you're sure that there's no other pressure?
That's an open question. So you don't know. As I was saying before, because the function is you are assuming that your functions are very expensive to evaluate, you may have a finite budget and say, well, I'm going to run and I'm going to compare this algorithm for 100 evaluations, and that's it. That's my comparison. You can come up with criterion with different criteria of stopping. You can do early stopping when you train neural networks. So, for instance, you can do things like, well, if I'm tracking the learning curves of the methods that I have, I can see how the curves converge and when I stop. That's an open question. Typically, you start with a finite budget that can be given in terms of the number of evaluations that you have, or that it can be given in terms of some work clock time that you want to fix, right? You say, I'm tuning my algorithms. I want to get the best of my algorithm in an hour, and then I just wait for an hour and I get the best one once everything is done. Right? More questions? So an example, I'm going to show you the for loop, the final loop, and then we'll have 15 minutes for different applications that I want to show you. So this is the function that I want to optimize, the dotted line. So this is the current best. The horizontal yellow line is representing the level of my current best. This is my model. This is one evaluation. And what I'm showing here is the normalized expected improvement. So I'm computing the expected improvement, right? And I'm normalizing it for visualization purposes, right? So I collect one point in the center of the domain, and I can pretty much collect any point here over here. The expected improvement is telling you, you know, we don't know much about the function yet. Here, you got something. I don't even know if it's good or bad because it's the first evaluation. So you can pretty much collect anything here or there. So we start collecting one point at one of the extremes. We say, OK, that's fine. And now look what happened. So we have collected one point in one extreme, another point in the other extreme. Look, because this value is higher than this one, the acquisition function is detecting that because you are making assumptions about the continuity of the function, the region that you discard here is larger than here, right? So you already see how the method is detecting that nothing interesting is going to happen somewhere over here because I have collected a very bad evaluation, but is relatively unsure of what is going to happen around here because the value of this evaluation and the value of my current best are very similar, right? So I have still two big regions where I have large uncertainty. So the acquisition is telling me, well, you can collect evaluations there to gain more knowledge about the function and the minimum, right? So I collect a point there. So the acquisition is telling me, well, it's fine, you know, but I still have this large region of uncertainty, right? And now is where the magic comes, right? So this is the decision where I collect the next point. I collect the point, and look what happens. Now the acquisition is automatically detecting that there is nothing interesting around here, nothing interesting around here, and that the minimum of the function should be somewhere around here, right? Why? Because, look, this is my current best. So this is my confidence bars for my model. So if I draw samples from my model, it's very unlikely that these samples are going to beat my current best. So my acquisition is reflecting that by saying, look, you shouldn't spend any evaluation here. You shouldn't spend any evaluation here because my model is telling you that there is no way that samples are going to go through regions that are going to be better than the current observations that you have, right? So now I say, focus here because I think the optimum is over there. So you collect a couple more of evaluations, and now you got it. You have collected and you have collapsed the information of the acquisition function around the location where the optimum of the function is, right? So instead of doing grid search blindly, instead of doing random search, what we have done is we have replaced the optimization problem by a few decision problems in which using Bayesian reasoning and using our Gaussian process model, we have reduced drastically the number of evaluations that we needed to hit the optimal location, right? Any question? So this is the core loop. This is the core example of how Bayesian optimization works. And this is obviously a very simple example, but you can think about having larger dimensional inputs and many other things. Questions up to this point?
If you have discrete parameters,
Yeah.
how do you deal with that?
That can be hard. So you have discrete parameters. You can do one hot encoding of the parameters and treating the parameters as a input, and treating the one hot encoding as continuous parameter and optimize those. Some people, when you have discrete parameters, some people uses discrete. Well, you can treat as a continuous and round. You have categorical variables. You can use one hot encoding. Some people like using random forest because you have uncertainties out of the model, but you can handle different type of variables very easily. But the problem is how the uncertainty of the random forest is calibrated. The uncertainty in GPs is better calibrated. So that's considered like an open problem in the community. It's not completely clear how you should do it. There are different hacks that you can use, but it's not completely clear which is the best way.
Talking about, sorry.
Yeah.
So talking about the discrete hyperparameter space, but the game of optimization is multi-abundance over large information. Then the problem would be as because our agents do labeling and like searching game, so that if we choose a Gaussian process for one type of continuous hyperparameter, even for discrete search, we still need to use Gaussian process, if you know what I mean.
That depends a lot on the problem.
We cannot use different model for different type of hyperparameter.
So most of the research in Bayesian optimization is about how to look the good acquisition functions that balance exploration and exploitation. I think the interesting part is more on how we do the modeling properly. What do I know about my problem? How do I represent what I know about my problem in a model that is able to capture all these things? And what's the influence that that has in something that I can do when I define an acquisition function and how I optimize it? So I don't know exactly the problem that you have in mind, but we can talk about it later, but probably you need to define properly a model to handle the optimization for it. We can have a chat about it. Okay? Yep.
At every step when you're adding new samples, you're updating your model, but you said before maybe that you're not updating your hyperparameters?
You can update the hyperparameters of your model. You may not need to do that after each single iteration. You probably want to do that in the first steps.
Right.
You may not to do that after a few steps because your model is going to be more consistent with the data that you have.
Is that, I mean, when you're adding samples, the model already changes? So is that a moving target kind of problem, or is it actually?
That's a decision that you have. The same way you need to decide the model, you have to decide what acquisition function you use. You need to decide how much you want to update your model. And that's interesting because so you are assuming that you are optimizing a very expensive function, right? Yeah. So now you have the classical AI dilemma that is, well, how much of the time I have I should spend on thinking and how much I should spend on doing, right? How much should I rely on a very cheap acquisition function that is maybe not very good, but that allows me to be more dynamical and correct more observations? You have an hour of time to solve my problem. How much should I spending a lot of time on thinking, which is the best evaluation, so I need to evaluate my objective less times. So that's a choice that you have to make.
So in all your illustrations, the measurements have been like noise free.
Mm-hmm.
We use this to optimize the
Yeah.
learning rate for the
Yeah.
network.
Yeah.
It's very noisy.
You can use a noisy version of the GP, and instead of like the expected improvement, instead of using Y, you can use the expected Y given the model that you have and derive the expected improvement. So pretty much the same. You can do pretty much the same things, although the definitions may change a bit because you are not basing things on Y, but you are doing things on the expected Y or on F.
This particular optimization, say my budget was 20 evaluations, and here I've used 8.
Yeah.
If I carried on using this model, I would keep progressing with that.
Probably, yes.
So what's this? Is a good strategy of dealing with that, making more random samples at the beginning of the...
For instance, or probably you want to stop and use your budget to do something else.
But I mean, so for example, we haven't really explored those two large areas.
So something you can do is, I'm not going to have time to go through that, but something you can do is to parallelize as well. So if you have budget in terms of the number of evaluations that you can collect, maybe you don't want to do things sequentially, you want to do things in parallel, right? So you want to run multiple samples at the same time and to update your model with your batch. Yep. More questions? I'm gonna show you. I want to show you a couple of demos. So basically, I'm gonna wrap up a bit. Although I had a few more things that I wanted to say, but so this is what you are doing. So you are transforming an unsolvable optimization problem, if you allow me to use that term, into a sequence of problems that you can solve using what you have in your manual of a classical optimization method, right? So that's all you are doing with BaseOp. So these are some take-home messages. This is important, and we have discussed already some of these. The model matters a lot, so you should integrate out the hyperparameters, don't optimize them. Optimizing the acquisition can be very hard, so you need to make sure that you are doing that properly, and that if you see a Bayesian optimization algorithm not working, please check that you are optimizing the acquisition right, because in many cases that's the issue that you have, right? And then be aware of the input dimension. So when you use Gaussian process with a stationary kernel, so as soon as the dimension increases, the model collapses, right? Because you are just modeling correlation about the points that you have observed, right? So the problem is that if you do Bayesian optimization in very large dimensions, if you don't use a very structured kernels in which you can propagate what you know about the function beyond the point that you are collecting, you may be in a case in which what you're doing with Bayesian optimization is some sort of a smart random search in which you are just collapsing uncertainty here and there if your space is very large, right? So these are the main take-home message. I know I'm the only thing. So how much do I have? Like 5-10 minutes. I want to show you a few applications in which you can use Bayesian optimization. Let me show you. Yep. So it's weird because I think I'm gonna cross this. Okay. There we go. So so this is an example that Mark Pulley put it together actually. So how can you use Bayesian optimization to solve reinforcement learning problems? So this is a notebook. I can share the notebook with you. So we have this example. So in this example, how many of you know this Montague kind example in reinforcement learning? So basically, the goal here is like I have a simulator of a car, right? And the goal is to push to optimize a policy, and the policy is I push the car right or left after a few episodes in which I run the game. And the goal is to define a policy that will make the car to reach the flag over here, right? So basically, if I mathematically write the problem, so this is the dynamics of the system that I have. So xt plus 1 depends on where the car is now. So the location at time t plus 1 is the location now plus how do I apply the force, right or left. And what I'm doing here is to say, well, I'm going to solve this other problem with some linear controller, right? So basically, I have a parameter that depends on the velocity, a parameter that depends on the position, and I have another constant. So I'm going to optimize this policy for a few episodes of the game just by learning and optimizing these three parameters, right? So and this is the final reward that I get after I have run the simulator for a few iterations, right? So if all I do is to apply some random linear controller, I just select the parameters of the policy at random, this is what happens, right? So nothing is really helping the car to reach the flag that I have, right? But now, look what happened if I use Bayesian optimization. So you are going to be using in the afternoon GPyOpt. This is GPyOpt code that I use to solve this reinforcement problem. The only thing I do is I optimize the parameters of my policy after 50 evaluations of the reward that I got in that episode, right? So I'm solving a reinforcement learning problem by applying Bayesian optimization to optimize the policy that I should apply to maximize the reward. I'm treating the reward that I get from this game as some black box, and I'm directly optimizing it using Bayesian optimization, building a model from the parameters. Sorry?
So are you optimizing parameters
of a linear controller.
Okay.
Yeah. So this is an example I wanted to show you, and I can share the code of this with you if you want. So another example is, so next week we are going to release some code about a library we have been working in. Mark and Andre, who is over there as well, are, I would say, the main contributors of the library. And this is a demo that we are going to release with the library that is about how you can use simulators and how you can use simulators to do uncertainty quantification, how you can use emulator of surrogate models to understand simulators that are representation of your real world. And a particular case of this is what we have been talking about today, about Bayesian optimization. And here, what Adam Hurst, who has been the intern working on this simulator, has created. He has created a simulator of a city. So this is a simulator of a city. We have cars. Let me see if I can make this bigger. So basically, we have a city. We can select the number of roads that we have in the city. We have select the number of cars. So if we want to optimize things like, well, imagine that I want to optimize the profit that I have if I have a taxi company with a number of cars. So basically, I can select a number of taxis in these cities, and I can run a simulation, right? So what you see here is the blue bars represents where the trips start. So I have a customer waiting for a trip here, and the blue line represents where a customer wants to go, right? So if I just have the simulator, this is my black box function that I want to optimize. Imagine that what I want to do is to optimize the profit in terms of the number of taxis, right? So something you can do, you can come here and you say, well, I'm running this simulation and I have this GP model for 20 taxis on the road and I have this profit, but I can go and say, and this is like the human Bayesian optimization that I was mentioning before. There is no acquisition function, but it's just me making decision about how many taxis should I use, which would be, I wouldn't have any guidance for that if I were just using the simulator, but with the emulator, I can actually visualize that with the Gaussian process, right? I can visualize that, and I can do things like sensitivity analysis with the emulator because I have gradients of the Gaussian process that I can get once I have just run a few simulations instead of running many of them using Monte Carlo, right? So I can come here and say, well, what happens if I reduce uncertainty and I run a simulation? And something that I really like is that you can really feel the pain of having some very expensive simulation, right? So you can change this. So these are taxis picking people. So this is something we are going to release next week together with a few tools to do Bayesian optimization, quadrature, essentially how to put machine learning models in a loop to make decisions under uncertainty. So we are going to start with a very soft release that we don't recommend you to use for nothing serious until we tell you to do so, because you may expect some changes in the API. And we will release the demo you will be able to play with as well. So I wanted to talk about many other things, but I know that I'm the only thing separating you from lunch at this moment. So if you have more questions, you can ask me during lunch. I'm going to be here in the afternoon during the lab. So yeah, so thanks for listening.
Yeah, do you want to go for lunch? Like,